But starting with a little bit of motivation, it's been, of course, a huge success for the cosmological paradigm. It's always lagging a little bit. Yes, with a multitude of various observations at different scales that all seem to be converging towards standard model for cosmology. But at the core of all of this success, there's, of course, the way we can see things, whether the glass is half full or half empty. And we may wonder if we're opening a whole plethora of new puzzles for cosmology and for physics in general. So there's in the core of all of this success, there's also a list of open questions that have emerged, and that's always how physics makes progress. A list of various questions from the very beginning of the universe to the late time of the universe and potential tensions that may or may not subsist in the future. So I'm not going to go through all of them in turn, but just as an example for the question of what dark energy is or what is at the source of the late time acceleration of the universe, I just thought it would be nice to illustrate the type of creativity that has been going on in the field in the past 20 years or so since observation of the late time acceleration of the universe. So this was in 2008, so already quite a few years ago. There was a list of potential models that Andrew Tolley, who will be giving a talk right after me, and myself provided. Provided the type of models I had come up since then in the literature. So I'm not going to go through all of them in detail, but then a few years ago, I thought it'd be nice to just illustrate what new models have come up in the literature since then. And what you'll see is that it's really been a huge explosion of various models that have been proposed in the past, even in the past 5 years or so. And this is not at all expected to be an exhaustive list of models. It's highly biased, but it's just suggestive in the type of creativity and imagination that people come up in trying to understand or address just the question of what dark energy is and how we can reconcile it with the cosmological constant problem. And there's a whole similar story going on for inflation at an even much higher level, or dark matter, and any open questions that might have come up in the cosmological paradigm that we're living today. So in parallel of trying to come up with solutions that are just within the standard model of particle physics and of cosmology, people have come up with models of modified gravity, and I've been asked to review a little bit of those. So I'm afraid I'm not going to make too much justice of that. But if you're trying to understand how you can modify gravity at all, there's various different type of assumptions that underlying behind general relativity that can be broken, whether it is the one related to Lorentz invariance. You can break Lorentz invariance, so you can restore, you can keep it. And if you keep Lorentz invariance, you can think of gravity as a spin 2 particle. It can be massless or massive. And if it is massless, then in order to modify gravity, typically you add additional degrees of freedom in which gravity is non-minimally coupled with the rest of the standard model or the rest of the matter field that be existing in the universe. So again, this is not at all exhaustive, but it's a type of classifications that can be used, and that is to address dark energy or any other question that you may have. Now, in all of those models, apart from maybe from the minimum massive gravity that breaks Lorentz invariance and some other Lorentz invariance breaking model, but in anything which is Lorentz invariant, you will introduce new additional degrees of freedom, no matter what you do. And in order to explain why we haven't yet observed those new degrees of freedom, you need to invoke some type of mechanism. So the simplest one would be to say that this degree of freedom, which I symbolically designate as phi, which may have some background, phi b, and it's living in a universe with a local density rho b. So one way to invoke that those degrees of freedom haven't been detectable yet is to say that they're weakly coupled to matter. So the coupling to matter is either 0 just from the outset, or there's some mechanism that sets it to 0 about some particular relevant cosmological background, for instance. So that's probably the most straightforward way to screen, or it's not really a screening, but you simply decouple this degree of freedom to the rest of the matter field that we may be observing. Now, in the past 15 years or so, maybe even more, I think probably 20 years, the chameleon mechanism has come up as one of a very powerful way to screen this the degrees of freedom that may be coming in, for instance, in FOVR, or in any other modifications of gravity. And effectively, what the chameleon mechanism does through non-standard coupling with matter is to give the scalar field in this context, but it can be applied to other things, is to give the field a large mass in dense environments of the universe. And then there's another whole class of models which are screened via another mechanism. So it's not directly through weak coupling, it's not directly through being very massive. The only other possibility is through its kinetic term. And as soon as you have a screening which relies in this case on a large kinetic term, which will mean that the scalar field, or whatever field you're considering, will effectively become weakly coupled to the rest of the matter field because it costs you too much energy to kind of excite it. This goes under the name of Weinstein mechanism. Sometimes the kinetic screening and Weinstein mechanism are separated out, but I really consider them all under the same umbrella. It is really when a kinetic term become large. And there's a whole class of models that I'm not going to go through that satisfies this Weinstein mechanism. But Andrew Tolley later on will be mentioning about some particular models and how this Weinstein mechanism gets implemented relatively naturally in many of these modifications of gravity and what the residual observable may be. But now for the rest of this talk, what I like to do is more of a generic approach where I'm not going to focus on any specific model at all, but I'm just going to motivate the fact that we have all of these effective field theories that may be interesting for the phenomenology of dark energy or for any other phenomenology that we want to have. And we really need to set these different type of effective field theories apart. And so the best way forward, of course, is what we always do. And what we should do is simply compare with the real world, and let observations and experiments tell us where we are within this region of effective field theories, in this region of parameter space among all the models that we have come up with. And this has done a lot of beautiful work already, just in the terms of the dark energy models that I mentioned. There's one example of observations that have been very useful in the past few years in segregating between various types of models, which is that of the direct detection of gravitational waves from a neutron star merger with an optical counterpart. And as I'm sure you all know, this has allowed the community to put a constraint on the speed of gravitational waves at LIGO frequency to be exactly the same as that of light at huge frequencies, in one part in 10 to the minus 15 or 16. And so by itself, this one observation has allowed us to roll out many models of dark energy, which would otherwise have predicted a different speed for gravitational waves. There's a small caveat here, which is not particularly relevant for what I'm going to be talking about today, but it's worth keeping in mind, and it still goes under the umbrella of this gravitational wave, this gravitational rainbow framework that I like to be talking about, which is that in all of those models, particularly the new ones that have been people have come up with in the past 12 years or so, they really had to be considered as effective field theory with a finite region of validity. And they are effective field theory which are designed to explain dark energy, which is, of course, effective field theory at a very low energy scale. We want them to be valid at scale of the Hubble parameter today, or roughly 10 to the minus 33 electron volt or so. Of course, we like them to be valid a little bit beyond that, but there's quite a gap between the scale of dark energy and the observations at LIGO scales, which are of the order of 10 to the 100 hertz or so. So there's quite a large gap between the two. And it's quite possible that some of those models of dark energy, even though they would predict a speed of gravitational waves that depart from that of light, they do so at very low frequencies. And as you go to higher and higher frequencies, the model of some of those effective field theory are no longer valid. They need to be embedded within a high energy completion. And we would expect, and there's some explicit examples where we can see that happening for scalar field theories, that whatever was responsible for the spontaneous breaking of Lorentz invariants at low energy, which is what leads to a departure from the speed of gravitational waves to be 1 at low energy, will go back to being precisely Lorentz invariant at high energy. Just in the same way as when you shine light through glass, you have a deviation from the speed of light going through glass at low energy, but as you go to higher and higher energies, light at huge frequencies still shines through glass or through water at the same speed as it would do in the vacuum, because it remains completely unaffected by the medium in which it's going through. And so you would expect the same thing to happen for these type of dark energy models. And so it's not inconceivable that it could still predict a speed which is exactly liminal at sufficiently high frequencies once we have implemented them within a consistent high energy framework. But still, using observation to constrain some of these dark energy model is already making a lot of progress. And just to give you an example, this is just an illustrative example that I'll be using throughout this talk, just so you can see where I'm headed. It's not necessarily the most compelling model in the whole universe, but if you just consider a model of dark energy or modified gravity, which goes under the name of the quartic Handesky, which will have parameter CB, CM, and CT. So T, for instance, is the speed of gravitational waves. This has been constrained to be 1 at LIGO frequency, but it's possible that at the scale of dark energy, you can still have a departure of the speed of gravitational waves as compared to 1. So this model, it doesn't matter too much what it is, has some free parameters, and you can use current observation, current cosmological observation from CMB, BAO, redshift space distortion, and everything to constrain where you're more likely to be in the region of parameter space. So this is relying purely on observations alone. Now, in addition to those observations, which I think should really be the core of all the constraints that we're imposing on ourselves, because this is really just comparing with the real world, this is really what we have. But complementary to that, you can also ask yourself some more theoretical constraints, which I would argue you can use to complement your observational and experimental constraints. So there's many different types of theoretical constraints that will go under this umbrella, but really it's asking ourselves how healthy the model that we're considering, particularly as a low energy effective field theory, will be. And particularly, you can ask yourself whether it's stable, whether it makes sense as itself, whether the degrees of freedom that you're using makes sense. And a question that is often quite hard to ask, but is really essential, is to wonder whether the model we're using is really valid in the regime of validity that we want to use it for. And so there's a lot of question about strong coupling or related questions, which are quite subtle to answer. But if you can't answer them, then you don't even know that you can use the effective field theory that you've written down to describe the phenomenology that you want to for that particular process. So to give you some example of how theoretical constraints can be used in complementary to observational constraints, if we go back to the Handesky model that I mentioned before, whether you like it or not, it doesn't matter too much. It's really just for illustrative purposes. In addition to these observational constraints, you can put this type of theoretical constraints, which are based on stability, which are based on some level of luminality as well, which we typically think are related to causality. And so this is to give you some example of how you can go from just the pure cosmological constraints, observation constraints, to the more theoretical constraints if you put them as a prior. So how you can reduce your region of parameter space where you would expect it to be. So what you can see in here is that the main constraint is actually coming from the speed of gravitational waves. You want them to be subliminal. And in many, as I mentioned, in many of those effective field theories, because you spontaneously break Lorentz invariants from the cosmology at low energy, you can have a deviation from the speed of gravitational wave to be 1. Now, the question I'm going to like to ask, I'm not going to put a poll in like Nick did, but I can ask ourselves the question, And this is typically done in cosmological effective field theories. Should we constrain a model so that the speed is always subnuminal, so that whatever we have as a phenomenology, this delta C, even if it's not observable, in principle should really be constrained to be subluminal so that we don't have superluminalities. So I'm not going to put a poll there, but you can try to answer that question for yourself. And if you were to ask me this question a few years ago, I would say the same answer to answer is yes, absolutely. You should constrain the speed of gravitational waves in the models so that the speed of gravitational waves is subluminal, because it's well known that superluminality is related to a causality. Even the tiniest amount of superluminality could be led to a macroscopic propagation outside the light cone, which would then be in tension with causality. So typically, this is where we are, and say that the sane thing to do is really to impose that the speed of gravitational is subluminal, and the speed of anyone, for that matter, to be subluminal. But now, what I'd like to convince you to do, and that will be through a different type of considerations, is that if you think of it a little bit more carefully, the connection between the presence of superluminality and the tension with causality is a little bit more subtle than what we naively anticipate, particularly in the presence of gravity. And so in the presence of gravity, it's not obvious that superluminality is always related to a causality. And to understand that, it's a little bit easier actually to go back into a yet different type of constraints, which are also theoretical, but it's slightly different than the constraints that I mentioned before, in how we can segregate between our various types of effective field theories. So before I mentioned about theoretical constraints, and those I really were thinking of constraints which were simply implementable within the low energy effective field theory, with no indication of how this low energy effective field theory will connect with an ultimate completion at high energy. But in addition to having a low energy effective field theory that may be describing whatever phenomenology that you want to, you may also ask yourself how this effective field theory came to be, what is its origin. And so you may have a model at low energy, but you like to see what is its fundamental completion at high energy. So I'm not going to give you the fundamental completion of quantum gravity and everything that, that comes to be. I'm sorry about that. But we can still impose some constraints on ourselves at low energy so as to ask that the model that we're having may in principle be embodiable within a high energy completion. And when I say these words, this may sound very familiar in the sense of that's what typically the swampland conjecture is doing. And so just to give you a perspective on how the considerations that I'll be talking about connect with the swampland or don't connect with the swampland, they're really complementary to them. So they're complementary arguments that are based on scattering amplitudes applicable at low and high energy, as compared to the swampland, which is a little bit more conjectural. So I'm putting a question mark here because I don't know exactly how those constraints live in slightly different space. So I don't quite know how to put it in that, classify it into that level of assumptions, but it's slightly different and yet complementary. So the constraints that I'll be talking about go under the name of positivity bounds, and they assume the notion that the model we have at low energy, no matter what it is, should be able to have a high energy completion, which is unitary in the sense that the probability sums up to 1. Locality, I'll mention a little bit more what I mean by this notion of locality. Poincare invariance, so not only I want Lorentz invariance, but I also want particularly time translation invariance and causality. So these are the assumptions that I'm going to impose on myself. You may be unhappy about some of those assumptions, but in the grand scheme of things, these are relatively non-controversial assumptions. Now, you can put more assumptions if you want to, particularly weak coupling, and you can go to higher and higher level of assumptions, all the way up to having an explicit realization at high energy, for instance, from string theory, if you wanted to. Or you can remove some of those assumptions, particularly when you want to implement them within a cosmological setup. But I'll start with this level of assumptions there. Another surprise is that we may have some models at low energy, which may seem to be completely consistent within themselves to fit all the possible experimental and cosmological and observational constraints that we are observing, and be theoretically viable at low energy, completely stable, for instance, maybe completely subluminal. It seems completely perfect at low energy. And yet for some of those models, we know that they will never ever be able to enjoy a high energy completion, no matter what this high energy completion is. So it can be string theory, it can be bubblegum theory, whatever you want at high energy. We know that those some of those models will never be able to be implemented within a consistent high energy theory, no matter what the field content is at high energy. I'm putting no constraints at high energy aside from the requirement of unitarity, locality, Lorentz invariance, Poincare invariance, and causality. So a priori, it seems to be kind of surprising that there should be such a strong connection between our high energy completion and the low energy effective field theory, because there should be a decoupling of scale between what's going on at high energy and what's going on at low energy. But the reason that why we can put some constraints actually at low energy from the requirement of what's going on at high energy is because of the notion of causality that manifests itself in terms of analyticity. I'll mention about that in a second. And this notion of analyticity is precisely what makes the connection between high energy and low energy. So I'll be a little bit clearer in that. So let's imagine you have a low energy effective field theory, no matter what it is. You can compute some scattering amplitude at low energy. I'll just be computing some 2 to 2 scattering amplitude. That's really just what you think it is at low energy. And I'll look at the complex energy square plane. Now, at low energy, I can compute this amplitude using this effective field theory, but my effective field theory will have a finite region of validity. So far, we have no theory for instance, for the standard model of particle physics or for general relativity, in that sense, that is embeddable all the way up to high energy. So we typically work within low energy effective field theory. You really need to go to string theory or alternatives to string theory to have some high energy completion. So let me imagine I'm working with a low energy effective field theory with a finite region of validity. I can compute the amplitude in that region. Outside this region, I can no longer use this low energy effective field theory to compute the amplitude, but the amplitude still exists. And there's still a meaningful amplitude which exists there. I simply can't use my low energy effective field theory to compute it. I need to implement new layers of physics, maybe new degrees of freedom that comes in, that have to be integrated back in, put it back in order for me to compute this amplitude explicitly. And there may be an infinite number of layers of physics that go up all the way up to ultimate high energy completion of everything. And I definitely cannot use my low energy effective field theory to compute the amplitude there, but it seems reasonable to assume that no matter what the amplitude is up to infinite high energy, it will remain local, Lorentz invariance, unitary, and also causal. A notion of causality manifests itself in this complex energy square plane as a notion of analyticity of the amplitude, which means we can make an analytic continuation between what's going on at infinite energy and what's going on at very low energy. So it's the notion of causality that really embeds the connection, the communication between what's going on at high energy and the requirement of, for instance, locality and unitarity at high energy to those at low energy. And I will put some constraints that have to be satisfied by our low energy effective field theories within the region of validity where we can compute them. So I'm not going to go through the details of those, but what we can see is that if we ask for ourselves for unitarity, Lorentz invariance, causality, and locality, and the notion of locality in here is the requirement that the amplitude doesn't grow up fast enough so that it satisfies the Froissart-Barn, and so that I can really go back into real space and ask ourselves some questions in real space. That's really what he means by that. So those conditions really imposes some condition on the imaginary part of the amplitude. One of them that we know very well is that the cross-section has to be positive. This is one of those realizations. And that within the low energy effective field theory is encoded within some statements about what the amplitude has to satisfy. So for instance, the second derivative of the amplitude with respect to the energy square has to be positive. And that is typically related to this condition of subliminality at low energy. And that seems to make sense because in at least non-gravitational affective field theories, we're familiar with the statement that subliminality is related to causality, or that causality should require subliminality. And there's an infinite number of other constraints that we can impose on ourselves at low energy. So this is just an illustration of how we can implement those constraints for physics beyond the standard model. I'm not going to go through that right now for sake of time. But if you go back into the model of the Quartic-Hondesky that I mentioned before with the 3 parameters, just for simplicity, then you can implement these observational constraints with the positivity priors. And this is to illustrate how powerful these positivity constraints are in further constraining the region of parameter space, complementary to observational constraints. So you can see that from this, for instance, region, yellow region here, imposing those positivity constraints tell you that you would have to be in this region. Now, this is just illustrative. It really has to be taken with a with a big spoon of salt, because there's quite a lot of assumptions that have been made in us being able to apply those positivity priors, which are not so easily satisfiable in the cosmological framework. So it's really just to see how complementary in principle you could the constraints from observations and from those positive priors would be. The reason why you have to take that with a pinch of salt is because as soon as you're dealing with gravitational affective field theories, and particularly with cosmological ones, there's a lot of things going on which have to be taken into account and that not necessarily under control at the current time. So in a non-gravitational affective field theory, I made a connection between those assumptions that you had at high energy and those notion of positivity bounds, and then a notion of subliminality, for instance, which seems to be naturally connected with the requirement of causality. Now, as soon as you're dealing with a gravitational affective field theory, as you want to do in the cosmological setup, then already the connection between causality and analyticity is a little bit more murky. Also, you may not want to impose the same level of locality at high energy. I'm still going to do it, but there's some open questions about those requirements in the first place. Hopefully, no one will object about the requirement of causality, but maybe that of locality you may do. But even assuming that those assumptions remain present, so I'm going to be as conservative as I can, even if you have those assumptions at high energy, deriving some positivity bounds from those assumptions is more subtle, and deriving the notion of subliminality speed at low energy from the positivity bounds or from the notion of causality is more subtle. There's an infinite number of reasons of why it's much more subtle, and I'm not going to go through this infinite number of reasons right now. There's a few reasons of why it is more subtle. The first one, related to the notion of subliminality, for instance, is just the fact that as soon as you have gravity, then you have frame artifacts, and this notion of speed is not invariant under the frame transformations, which the notion of causality is. So this is a completely trivial frame artifact that we can deal with because I have a finite time. I'll say this is something too easy for us to discuss about today. It can be very easily taken into account, but this just tells you that simply stating that the speed has to be subliminal in relation with causality makes no sense when you're dealing with a gravitational theory. You need to specify which frame you want to be working with. Now, a much more difficult problem to address is the fact that if you're interested in cosmology in particular, or whatever else you're interested in, the cosmological background will spontaneously break Poincare invariance. And so you really need to understand how the notion of the breaking of the symmetry will be implemented within the new positivity bounds, which were used assuming Poincare invariance. So this, for now, is going to be too hard a problem for me to solve. I'm not going to talk about it right now, but there's been some progress made by various members of the community. I think there's still a way to go into understanding precisely how to implement these constraints in a background that spontaneously breaks Poincare invariance. Now, a third type of subtlety that emerges as soon as you including gravity, and I have to say none of those are related to the fact that we don't have an ultimate quantum theory of gravity at high energy, or we don't have an agreement of what the quantum theory at high energy is. All of those are just artifacts at low energy already. But the third reason why it's becoming more subtle is because of the presence of a gravitational exchange, an exchange which is mediated by a massless spin-2 particle that arises as soon as you're dealing with gravity. And as soon as you're dealing with gravity, as soon as you add gravity in the game, you may not be interested in gravity per se, so you may be interested in scattering fermions, for instance, for physics in the standard model, or physics beyond the standard model, or you may be interested in scattering of your inflaton scalar field or your dark energy scalar field. It doesn't matter too much, but just the fact that ultimately it is a gravitational theory means that you can't prevent gravity to come along and play with you and to have a process that includes a gravitational exchange. Now, this gravitational exchange, because it's mediated by a massless particle, will have a pole at zero mass, because it's a massless particle. So when T is the momentum transfer is zero, you have a pole there. And that happens even if you had an exchange of a photon, that's okay. But as soon as you're dealing with gravity, because it's spin-2 particle, the residue of this pole grows like the energy to the 4, like s squared. And that means that as soon as you have gravity, this contribution does affect the second derivative of the amplitude at t0. And it spoils the direct applicability of the positivity bounds as soon as you have this pole. If you had a photon, this would just grow like S. So even though technically you have a pole at T0, that doesn't come into this type of bounds. But now analyticity technically is much more subtle to understand at T is equal to 0. What it implies in practice is that as soon as you have a gravitational theory where those type of bounds are present, instead of us being able to impose a positivity bounds, which was just this coefficient being positive, in all the examples that we can think of explicitly, for instance, a model of particle physics minimally coupled to gravity, for instance, QED, minimally coupled to gravity, we see explicitly that this coefficient C is not positive. It's actually negative by an amount which is suppressed by the Planck scale, of course, so that when you decouple gravity, you send the Planck scale to infinity, this goes to 0, but it is still negative technically. And the very presence of this negativity is actually crucial in understanding the connection between causality, or how causality implements itself at low energy. Because as I mentioned before, in non-gravitational effective field theory, it is through the notion of positivity bounds, through the requirement that this quantity here is positive, that the notion of causality really manifests itself under the statement of subliminality within the low energy effective field theory. And this is how it's been proven, for instance, for the speed of light at low energy when it goes through different type of media. Now, in gravitational effective field theory, because the equivalent of this quantity here does not need to be positive definite, it can be a little bit negative, not by much, but it could be in principle a little bit negative. This tells us that the notion of causality doesn't require, even putting aside any frame artifact, doesn't require the speed of gravitational waves to be strictly subliminal. A little bit of subliminality is actually allowed, so long as it's suppressed by the Planck scale and sufficiently suppressed by the Planck scale. So as soon as we get to that level, you may wonder, well, if that's the case, how would that be visible? How the notion of causality manifests itself within the low energy effective field theory? Because after all, as soon as you have the tiniest amount of subliminality, and it can be suppressed by 120 orders of magnitude, it doesn't matter. In principle, the smallest amount of subliminality at low energy still means that you can integrate it out till the end of the universe, till the end of time, and get macroscopic support outside the light cone, which itself would tell you that you're in violation with causality. So within the next 5 minutes or so, if I have the time that I have left, let me just try to argue on how this small amount of subliminality that manifests itself within gravitational low energy effective field theory, particularly cosmological ones, is still consistent with a notion of causality, or not in tension with causality. So let me emphasize once more, and that once again, that and this is within the realm of the gravitational rainbows, that the speed of gravitational waves, just like the speed of light, can vary as a function of frequency when it's implemented within a spontaneously breaking Lorentz invariant medium, like cosmology. And so at high energy, at infinite frequencies, the speed, the phase velocity, infinite frequency phase velocity is the front velocity, can remain luminal. So there's no tension about that. There's no discussion about the fact that the infinite frequency phase velocity is luminal. And this is really what the requirement of causality asks us, that the front velocity be luminal. But within the low energy effective field theory, what we probe is not the front velocity, is a low frequency phase or group velocity. And we'll have to understand how this low energy superluminal velocity can be consistent with causality. So if we take the example of a cosmological framework with an effective field theory that may include, for instance, higher derivative terms as an effective field theory, so those are okay as an effective field theory, you will have inevitably some operators that lead to a departure of the speed, of the luminal speed of gravitational waves, plus corrections at high energy. So those corrections at high energy are precisely the ones responsible for switching the low energy phase velocity from subluminal to or superluminal to being exactly luminal at a higher frequency. But at lower frequency, you have a departure from luminality, and a priori you can integrate this level of superluminality from the beginning of the universe all the way up to the end of time, so that even if you have a very small amount here, you'll have a large amount support outside the light cone. And then you can perform at infinity, you can perform a boost and then go back in time and stop this talk before it ever started. Now, the reason why this is consistent with causality is because we're dealing with a low energy effective field theory. And as a low energy effective field theory, it has a finite cutoff. To be conservative, the cutoff will be at least at the level of the Planck scale. In most cases, as I mentioned, it can be much, much lower, maybe even lower than LIGO scale. But to be conservative, it will always have to be smaller than the Planck scale. Now, in those models, this level of superluminality is not big, it's not even observable, but it's a proof of principle on whether or not it could be a priori superluminal. You have this level of superluminality. Now, if you wanted to integrate from the beginning of time or from a given time all the way up to infinity, you need to make sure that you remain within the regime of validity of your low energy effective field theory throughout this time. And remaining within the regime of validity of this effective field theory tells you that there's maximum frequency that you can use for the modes that you can use which depends on how early in time you want to go. Or in other words, if you want to start at a given time ti, because the curvature at that time is larger, it means that you need to use lower frequency modes to send it. Otherwise, for too high frequency modes, you will go beyond the regime of validity of the UFT. Or in other words, the wavelength that you need to include or you can use to probe this support outside the light cone has to be larger than the Hubble parameter at the initial time in units of Planck scale. But when you use this requirement, which comes from the validity of the effective field theory, into account, and you try to integrate out the distance outside the light cone that you can have, in principle, maximum distance that you can have from this level of superluminality, you end up seeing that it will always end up being an amount which is smaller than the physical wavelength of the mode that you sent in. So in other words, yes, in principle, you can have a support outside the light cone, but it's not resolvable. It's always smaller than the physical wavelength of the mode that you use to probe this level of superluminality. And so using a particle approximation to make these measurements is no longer adequate. You can't do that. So there's never really any physical support outside the light cone in the sense that it's never resolvable. And because it's never resolvable, there's no violation of causality. And this is the case in an example of cosmological setup, but you can do the same thing for other type of effective field theories. And you can do the same thing about, for instance, black hole or other type of configurations that would spontaneously break Lorentz invariance. Now, a priori, you may say, well, this statement by itself simply tells you that it's not resolvable, and so it's inconclusive. But it's actually better than that. The very fact that it's unresolvable tells you that the would-be secular effect, or the secular effects themselves, can never grow, and therefore you can never grow as to be dangerous. So they're always remaining under control. So this quantity here is always going to be much smaller than 1. This is exactly what the notion of unresolvability tells us. And if this is always much smaller than 1, those corrections here, that comes in when you're trying to expand this exponential in terms of what the exponential would be using the standard flat space-time propagator, and then corrections from the fact that you are seeing some departure from subliminality. The fact that you can do this perturbative approach without those secular effect growing up tells you that you can compute the retarded propagator perturbatively about the one which wouldn't include the EFT operator, so wouldn't account for this spontaneous breaking of Lorentz invariance. And perturbatively, if you start with a retarded propagator, which is 0 outside its light cone, perturbatively, you can never all of a sudden create a retarded propagator which will start having support outside its light cone, because all you're doing perturbatively is acting operators on something which is 0 outside the light cone. So by itself, the notion of unresolvability of the support outside the light cone is then directly related to that of causality. So I'll stop here. This is just to motivate the fact that we have to be a little careful when looking at constraints on low energy effective field theories, particularly in the cosmological setup. So there's been a plethora of gravitational effective field theories describing various time evolution of the universe, and I've seen there's going to be many talks about that throughout the rest of this conference. What I like to argue is that complementary to the huge success of observational constraints, which are becoming more and more precise, we can also invoke some level of theoretical constraints. There are some theoretical constraints which are directly embeddable within the low energy effective field theory without any priors with what happens at high energy. Now, the more priors you put on yourself from high energy, the more constraints you will have at low energy. But even just remaining relatively conservative on what's going on at high energy, so I'm not going to be very specific on a particular string theory compactification, for instance, just requiring that whatever happens at high energy, no matter the number of fields, it can be an infinite number of higher spin fields at high energy, no matter what happens there, it's going to need to be unitary, for instance, and causal, is related to positivity bounds. Now, those positivity bounds is typically what tells you that the speed at low energy has to be subliminal, but in the gravitational context, it's a little bit more subtle than that, and a small level of what you typically qualify as subliminality is allowed, and so that has to be taken into account when segregating between various types of effective field theory, particularly for the cosmological setup. Thank you.